Welcome to the screencast for the fourth problem in the 2013 Winter 2 Computer Science 121 Practice Final. Now, I mentioned for this particular problem when I was doing the intro to the exam, if I came across this problem with all this text that I need to read and I hadn't already read the text and had a sense of what it said, this is a problem I would seriously consider skipping. And in that review, I actually said that I would do C, D, and E first, and I would come back to A and B, because it looked like for A and B, I was going to have to read through all of this and understand it. But C, D, and E looked like things I could maybe solve without reading all of it. So what I'm going to do actually is skip ahead and try to solve C, D, and E first. And then I'm going to come back to solving A and B. And I'm going to do those as separate screencasts. So this is actually the solution to C, D, and E. And the solution to A and B is going to be in a separate screencast. So let's jump ahead now to C, D, and E. Okay. If a long int, whatever that is, on a particular computer takes 32 hexadecimal digits to represent, how many bits long is it? Okay, if a long int takes 32 hexadecimal digits to represent, how long is it? Well, actually, we don't necessarily know precisely how long it is. Every hexadecimal digit can represent up to 4 bits, but imagine that something were 6 bits long, like this. Here's a 6-bit long number. To represent that as hexadecimal digits, I'd chunk it into 4-bit pieces. And if I had any left over, like I do here, I'd just fill those in with zeros. Right? So here's my zeros, my ghost zeros at the start. And then I translate each part. So this is 9, and this is 1. So this would be hexadecimal 19. So I'm actually not going to know exactly how many bits long it is, but I'm going to know pretty close to how many bits long it is. So let's erase what we've got here. See if I can erase these dotted lines that I drew. That's annoying sometimes. There we go. Okay. So 32 hexadecimal digits. Each hexadecimal digit can represent up to 4 bits. So this is 4 times 32, which is 8. 4 times 3 is 12. 128 bits, probably. But it could theoretically end on the left-hand side with maybe just 1 bit, right? And then the extra bits, the 1, 2, 3 extra bits, we would just fill in. So maybe, or maybe, it's only 125, 128 minus 3, or 126, or 127. But that would be really unlikely. We're probably going to have something that's a power of 2 as the length of this long int. So I think 128 bits is my answer. And if I really want to state my assumptions, I'll say I assume the hexadecimal digits are fully used. So let's just... yeah, that sounds good. Let's move on to part D. Roughly speaking, a floating point number is like the fixed point representation we learned, plus scientific notation, i.e. multiplied by 2 to the k, where k is specified as part of the value. Okay, so it's a fixed point number, but we can shift the binary point, if you like, the equivalent of the decimal point, around. Do I think Java's float and double types can precisely represent 1/11th? Why or why not? So there's not really any connection to this starting part here and the ending part here unless Java's float and double types are floating point numbers. Given that it's called float, I'm going to assume it is a floating point number. But let's just double check quick. I'm just going to skim the Java specification, which I think was given up above somewhere. That's C++. The Java language specification has the following to say about its numeric and Boolean types. The integral types are byte, short, int, and long, whose values are 8-bit, 16-bit, 32-bit, and 64-bit signed 2's complement integers, respectively. And we know what all that means. We know what a sine 2's complement integer is. We know what it means when it's 64 bits long, or 32, or 16, or 8. So that's all good. And char, whose values are 16-bit unsigned integers. Okay, so they're not signed. Representing UTF-16 code units, whatever that is. Presumably it's described in section 3.1. So let's just not worry about that part. But that hasn't told us the answer to our question yet about floats and doubles. The floating point types, there we go, floating point types are float, whose values include 32-bit IEEE 754 floating points numbers, whatever that means, but they're 32-bit floating point numbers anyway, and double, whose values include the 64-bit IEEE 754 floating point numbers. And then the Boolean type has exactly two values, true and false. So let's jump back down. We know what we need to know. Float and double are floating point numbers. One of them is 32 bits long, and the other is 64. Do I think they can precisely represent 1/11th? Why or why not? Well, in our fixed point representation, can we represent 1/11th? We could try to answer that question by doing the Scottish or not thing that we did in the slides, where we said, okay, we want this person here to be 1/11th Scottish. And we can control the mom's Scottishness, but not the dad's. Dad is either all Scottish or all not Scottish. In this case, we'd want dad to be not. And then mom is going to be twice as Scottish, right? So this would be 2/11th. And then we would just keep going on. And if we get a repeat, then we know we're going to get repeats forever. So we'd be looking for a point where we come back to 1/11th. And that would show that we have a repeating representation. Kind of like the representation for 1/3 or 1/6 or 1/9 in base 10. Okay. But that also sounds like a fair bit of work. Let's see if we can figure out a simpler way to do this. Well, we also mentioned that every single fixed point number that we created is some value on top, some value I, say, on top, divided by 2 raised to some power. And that's not going to change here because we're just multiplying by a power of 2. So we can change this power of 2 on the bottom here, but that doesn't affect the thing on the top. So we're still going to have some integer I up top divided by 2 to some integer n. So can we represent 1/11th in this format? And that comes down to, really, can we take 11 and multiply it by something and get a power of 2? And the trouble is, we're not going to get a power of 2 when we multiply 11 by some integer, unless 11 already is a power of 2. So basically the only things we can represent here are fractions where the denominator is a power of 2, and 11 is not a power of 2. So the answer is no, we can't represent this. No, because 11 is not a power of 2. So the representation requires an infinite number of bits and floats and doubles have 32 and 64 bits. Okay. So finally we have, if a Java Boolean were actually represented in the computer using the same amount of space as a byte, how many wasted bit patterns would the representation have? A wasted bit pattern is a pattern that means nothing, or that has the same meaning as some other pattern already counted as not wasted. Okay, so wasted bit patterns are the ones we're not using, or we're using but they're repeats of things that we've used before. We already saw above that Booleans have exactly two values, true and false. Bytes, let's just double check, but I imagine a byte is 8 bits, as is the standard definition of byte. A byte is 8 bits long. Okay. So we have an 8-bit representation used to represent just the values true and false. Well, we only need 1 bit for true and false, so we have in some sense 7 wasted bits. That's not what's being asked though. It's asking how many bit patterns are wasted. Well, how many bit patterns are there in 8 bits? There are 2 to the 8th bit patterns in 8 bits, which is 256. We're using 2 of these. Everything else is either unused or it's a repeat. So wasted patterns, if you want to think of them that way, are 256 minus 2, which is 254. Okay, and that's it for parts C, D, and E. I'm going to solve parts A and B in a separate screencast.